Monday, Tuesday.
I don't know. I'm kind of old and I'd probably end up like in a prison or something. All right, so here we go. We're going to pick up where we left off yesterday, which is I will turn back some homeworks too, so you have this. We are, let me stay awake. And according to my records, we're ready for number 5, which is another Gauss. Oh, so are we ready for a calculator problem? Yeah, it says solve on calculator using Gauss-Jordan reduction. Okay, all right. So do we remember what that means? What are you doing?
Throwing my gum. Oh, sure.
All right, here we go. If we're doing Gauss-Jordan reduction, we're going to write down the matrix and going into my calculator. Last time, we talked about using Gaussian elimination by hand, and that's when we got zeros. Remember that process? Well, now I'm telling you to do it on your calculator with Gauss-Jordan reduction, which means we're going to put that matrix into our calculator. So second matrix over to math. How big am I putting in? 3 by 4. Remember, some of you missed this in the homework. Dimensions are rows by columns. So this is a 3 by 4. And I'll put these numbers in. I need all of you to be doing it with me. And then after you get it in, go ahead and second quit. Go back out. Now, Gauss-Jordan reduction, that word reduction should remind you of reduced row echelon form. So that means if I were doing it by hand, which I'm never going to ask you to do, you would have to find these zeros and these zeros, right? But we're going to let the calculator do that. So we go back into second matrix, click over to math, all the way down to RREF, and then second matrix A. And I got this. Anybody else get that?
Where do you find the RREF?
Second matrix math, same place it was yesterday when we talked about it. Now, ideally what happens, guys, in a perfect situation, what happens is you get something that looks like this. This is the best case scenario. This is what happened the last time we RREF'd on our calculator. This literally says x equals 3, y equals 4, z equals 5. Right? That is the best case scenario. That's all 3 planes coming together in the corner. That point right there. That's perfect. That is not what happened. The last problem we looked at yesterday came out, I don't remember, but something like this. Well, it came out like that, not like this. And what did we say that meant?
No solution.
That meant no solution, because this, when it looked like this, it said z equals 1. When it looks like this, it says no z's equal 1. Well, that's not possible. So we said our planes have no common intersection, the 3 planes. Well, what in the world does this one say? Literally, Elaine.
That one of the planes is the same plane.
Oh, not quite, but you're close. It says, literally, this bottom row says 0z equals 0. Remember, when there was a 1 here, it said z equals 1. When there was a 0 here, it said no z's equal 1. So this one says no z's equal 0. Well, tell me what z can be. Anything, right? Root 17, 113, negative 83/7. It can be anything, right? So we're going to indicate that by saying z is z. That's how we indicate that. Z equals z. So pick it. Z can be 5, z can be 8, z can be anything you want it to be. But now, go up a line. What does this line say? We've established z can be anything. Well, what about y? Well, y minus 2z equals negative 2. Right? Which means y equals negative 2 plus 2z. The value of y depends on the value of z that you chose. So if you choose 5, remember, z can be anything, so pick your number. Z is 5, then y would be 8. But if you picked a different z, you'd get a different y. Right? Okay, well, what about the top line? X plus 3z equals 5. So x equals 5 minus 3z. So again, your value of x is going to depend on your value of z. So how do we organize this, and what does it mean? Well, the way we organize it, there are 2 possibilities. I'll show you both of them, no matter which one you use. One possibility is, since we're in a matrix format, we'll keep the matrix format and say x, y, z as 2 parts. Look, 2 parts, a number part and a z part. So we'll have a matrix for the numbers, and we'll have a matrix for the z's. So x, for example, its number part is 5, and its z piece is negative 3. You see how I did that? Well, what's y? His number part is negative 2, and his z part is 2. Well, what about z? What's his number part? 0. What's his z part? 1. Not 0. 1. That's 1z. Z is 1z. This is called, well, both formats. This is called the general solution, because this describes how many points. Infinitely many, depending on what you let z be. It's called the general solution. It shows the relationship between the variables. Pick a z, and that will determine your x and y. The easiest particular solution, what we call a particular solution, the easiest one would be 5, negative 2, 0. Because that's the point you get if you let z be 0. If you let z be 0, you don't have this, right? All you have is this. If you were asked for 2 particular solutions, well, you can use that one, always that's 1. What would you have to do to get another particular solution? Pick a z, pick a different z. So if you let z be 1, then you could do 5 minus 3, and negative 2 plus 2, and 0 plus 1. And that would be another particular solution. But there are infinitely many of them. You can let z be whatever you want. All right, so one way to write our answer, before I start erasing all of this, when you use Gauss-Jordan reduction, your matrix has to be in reduced row echelon form. Look at this matrix. Remember what the qualifications for reduced row echelon form are. The first number in every row that isn't a 0 has to be a 1. Got it. Everything under those 1s is a 0, and everything above those 1s is a 0. Do you see how that's in reduced row echelon form? Even though it doesn't look like normally they look, it is. Okay. The other way you can write your answer, if you choose, is horizontally. So XYZ equals a point plus Z times another point, or another 3-piece coordinate. So X is 5 minus 3 Z's. Y is negative 2 plus 2 Z's. And Z is 0 plus 1 Z. So these two things are exactly the same. No one cares how you write it, but you gotta write it one way or the other when you end up with a matrix where you lose a row, basically. Your bottom row, all zeros. Does that look familiar to anybody? Joseph? Oh my goodness! Let me come back and change this to a T. And change this to a T. Aren't those, isn't that the parametric equations? I mean, aren't those parametric equations? And when we wrote in two dimensions, when we wrote the parametric equations of a line, it was something like this. And we said x equals 1 plus 2t, or 3t, and y equals 2 plus 4t, remember that? This, guys, is a line. That is what the equation of a line looks like in 3 dimensions. This is a point on the line, and this is the direction vector slope of the line. This is a 3-dimensional, so is this. This is the 3-dimensional shape of a line. When you write lines in 3 space, this is what they look like. This is a point on the line. This is a direction vector. It describes how the line moves through space. So wait a minute. Remember how this problem started? 3 planes, right? Started with 3 planes. Our job was to figure out how they intersected. How did these 3 planes intersect? In a line. Can you visualize that? What's happening? 3 planes intersecting in a line. Here, behold these for me. There's a plane. Here's another plane. Hold it flat. Hold this one. Like this, okay? Hang on to it. I'm gonna like that. There we go. So there's 2 planes intersecting in a line. Here comes the 3rd one. That's what's going on here. You have these 3 pieces of paper, but they're all intersecting in like a crease, like the pages of a book. 3 pages of a book that all have that same line in common. Oh my gosh, thank you. Isn't that a magnificent idea? Okay, let's try the next one. Solve on your calculator. You're going to do exactly the same thing and see what kind of solution you get. As I'm erasing this, remember those particular solutions we got down here? Those are just points on the line. There are infinitely many of them. There's points on the line. Ups, ups, ups. Be careful here. What do you notice about this system? We have X, Y, Z, and W. And the letter's missing, just the 0. basketball game, but it's soccer last night, I guess. Well, when he emailed me, they were going to get checked, but he thought it was broken, I'm not sure. But it wasn't the basketball game, it was, the soccer. All right, you got this typed in? Matthew, have you typed it in?
Oh my God, I did it.
Oh, that's a sad state of affairs. You on the board, 50-cent rental. Gotta have a calculator. Sam? You owe me 50 cents from last time. I'm used to doing these in some of my classes, calculator checks. I shouldn't need to do calculator checks in an honors math class. We should have our calculator. It should be functioning. Remember, boys and girls, if you don't have a calculator, you can go to the library and check one out. There really isn't no reason. Open it up. The whole idea is we're using our calculator. Okay? So you don't need to have him do it. You can do it. All right. Did anybody get this typed in? Hit RREF and come up with a matrix. Who came up with something? I've given away all my calculators. Charles?
For the top row, 1, 0, 1, 2, 1, 0, 1, -2, -1, -1, 0, 0, 0, 0, 0.
All right, let's be clear about something. We have added a fourth variable. So now we've gone into 4 dimensions. So I have no geometric interpretation for you here. We're just doing a pure math problem, and we gotta come up with a solution to this system. Key RREF, so my expectation is that that matrix is in reduced row echelon form. Is it in reduced row echelon form? Yes, but it's got a ton of numbers, right? A ton. Now the first thing, and I noticed this right off the bat, I don't know if you did, this system has more variables than it does equations. Did you notice that? Usually, like the last one we did, even though it got wonky at the end, it started out with 3 equations and 3 variables. That's how we like it. This is kind of not good. So I'm going to arbitrarily stick another row on the bottom because I didn't get a 4th equation. Is this a true equation? This thing I added on there, is it true? Is this equation true? No x's, no y's, no z's, no w's, add up to nothing. That is a true equation. And that's going to help me build my solution. Because last time, we decided z could be anything. Well, actually, that's still the case. But also, w can be anything. So I'm going to start with w equals w. And then I'm going to say z equals z. Because that's what these 2 equations tell me. In the end, I have to be able to account for all 4 variables. So I'm going to say, I don't know what w is, it can be anything, z can be anything. Well, tell me about this. Y minus 2z minus w equals -1. Would you agree with that? So what does y equal? -1 plus 2z plus w. Uh-oh, my goodness, okay. You're thinking about what your answer is going to look like now. Well, let's do x. X plus z plus 2w equals 1. That's what this tells me. So x is 1 minus z minus 2w. Well, I have to add something that's true, and that is true. I could have put numbers in there because I don't have an equation for that row, so I just added in all zeros. It's true, right? And I needed to do that. What?
Because you can't put a 0 on there.
You have to put a zero
Yeah.
on the ones. And these two ones, yeah.
Yeah.
Yeah, those would have to be zeros. So what I added, this one came out of the calculator. This is the one I added, because I have to account for my W. Yeah. So now, what does my answer look like? Well, if I write it in matrix form, I'm gonna have an X, Y, Z, and a W. I have to account for all my variables. But now, look at this for example. How many pieces does Y have? 3. So I'm gonna need a column or matrix for the numbers, a column for the Z's, and a column for the W's. So X will be 1 minus Z minus 2W. Are you following what I'm doing here? Y is negative 1 plus 2Z plus W. What's Z? What do you think Z is? 0, 1, 0? Z does not have any W's, does it? And then what's W? 0, 0, 1. Okay. How am I going to find, this is the general solution. How am I going to find particular solutions for this one? If somebody says, okay, find one point these all have in common, one particular solution. Points kind of, I'm using that word loosely. Whatever it is, it's going to have 4 variables to it, so find one particular solution. How would I do that? What would I have to do? I have to pick a Y, or pick a Z and a W. Now, obviously, if I let them both be 0, which is possible, I can let both of these be 0. Then I'm going to have 1, negative 1, 0, 0 as my particular solution. But if I want another one, I'll have to assign those things whatever variable I want, or whatever number I want to use. So maybe I'll let Z be 1 and W be 2. Could I then figure out the X and the Y that would match up with that? Yeah. These would be particular solutions. This is the general solution. It can be written sideways too, like the other one was. The difference is, in 3 dimensions, we often write them sideways because that's how you write the equation of a line. This is the equation of I don't know what. So you can write it sideways, but there's really no compelling reason to do that, but unless you like it better, you can always write it sideways. I'll tell you what, I am fascinated by that. All right, we did one of these, the next problem, we did one of these the other day. Solve using the inverse method on your calculator. Solve using the inverse method on your calculator. Now, let's catch our breath. I know I'm pumping so much information your way. Remember, what we did by hand yesterday was called Gaussian elimination. We did that by hand, getting those zeros. What you've done today so far on your calculator is called Gaussian reduction. Now we're going back to the inverse method, which we talked about and actually did an example. I added it in the other day, a couple days ago. Let's see if you remember what you need to do if you are using the inverse method. If you're using the inverse method, what do we need to do? Anybody remember? in a 2 by 2 is gonna be bigger than that. That's not, finding the inverse of a 3 by 3 by hand is tougher. Luckily, we're using our calculator. So we're not flipping anything. We're letting the calculator do all of the actual work. But we have to feed something into our calculator. If we're using the inverse method, remember A, or some, I'll just say A, is the matrix of coefficients. So 3, negative 3, 6, 1, negative 3, 10, negative 1, 3, negative 5. That's the matrix of coefficients. B is the constants. Is this starting to look familiar now? If you're using the inverse method, this is what we do. So we're gonna put this in as matrix A, we're gonna put this in as matrix B. Then what are we gonna tell the calculator to do with those matrices? Do you remember?
Inverse A multiplied by B.
Exactly. This is gonna give us our answer. So we put in A, we put in B, 2 separate matrices.
Interruption. Please then make Murphy inconvenient or towards the end of the period.
Yeah. So, Meg, do you know what this is about? All right, why don't you run down there in case it's something important. Okay, A inverse times B. All right, so you got A in, you got B in. You know how to do that part, right? Everybody's got those in. What are the dimensions of B, by the way? 0 by 1. Okay, once you get them both in, if you've forgotten what to do, you do second matrix, and then just hit enter, and that will pull A up on the screen. Names is how you get your matrix on the screen. And then you press your inverse button, which is your button that looks like this. It's right there on the calculator. Then times, second matrix, click down to B, hit enter. Again, I think. What did it come up with? It should have come up with a matrix for you. What is it?
18, 1, 18 over 3, 14. 118.
Like that?
No, 118.
Okay, tell me the top number.
18.
Okay, what's the middle number?
118 over 3.
And the bottom number?
14.
Is that what everybody got? Did anybody else get that?
Yeah.
Okay, so I'm gonna assume that's the right answer. If you didn't get it, go back and double check what you put in. This is the inverse method. Okay? Number 8, determine A, B, and C so that these points are on the graph of this. So in other words, what are we doing? It's called polynomial curve fitting. We're taking 3 points and we're going to write the equation of the parabola that goes through them. Right? You had lots of practice writing the equation of lines. 2 points, write the equation of the line. Now we've got 3 points, we're going to write the equation of the parabola. Well, why in the world is this in section 7.3 of the matrix chapter? Now let's talk about this for a second. If this point is on this curve, then shouldn't I be able to plug this in for x and this in for y and have it be a legitimate equation? All right, let's do it. So 5 equals, and I'm putting in negative 1, so it'll be a minus b plus c. And then I'll put in negative 1 for y and 2, so that'll be 4a plus 2b plus c. What's happening here? What am I generating? I'm going to plug in my third one now. What have I got? A system of 3 equations, 3 unknowns? Isn't this the same as x, y, z equals, right? So how do you want to solve it? Tell you what, I don't care. You pick it. So you use your calculator and you're going to solve it either probably by doing this or by using your RREF button, using Gauss-Jordan reduction. But I don't care if you have something else you want to do, go ahead. But let's all solve this system so that we can write the equation of the parabola that fits these 3 points. David?
When we make the matrix, do you want us to put the part that's like equal on the back?
Yep. Yep, and if you're doing the augmented matrix, yes. You want to turn your equation around. You could also do this by hand if you just love Gaussian elimination, getting the zeros and all that. You could do this by hand that way. If I still had a calculator, I personally would probably do this. Does everybody understand the equations, by the way? Everybody's figured out where they came from? Plugging those points into the general form? I'd probably do that and then RREF it. Anybody else doing that? Seth, you got it done? 1 0 0 0 1 0 0 0 1. What's my last column?
4, -6, -5.
Before we talk about the answer, I want to make sure somebody else got that. Anyway, somebody else got that. Okay. So what's the answer? What do I write in the answer blank? The matrix is not the answer. That's my work. That's how I arrived at my answer. But what's my answer going to be? Y equals, or f of x, doesn't matter. F of x or y equals 4x squared minus 6x minus 5. That's the equation of the parabola, the quadratic function that contains those 3 points. Everybody okay with that? I know what you're all thinking. Miss Ford, just shut up. Nope, not gonna do it. We have more work to do. All right, let's look at the last one on this page. Here we go. We have 3 silver alloys on hand. One is this much, another's this much, another's this much. How many grams of each alloy is required to produce 80 grams of a new alloy that is 34%, if the amount of 30% used is twice the amount of 22% used? Oh my gosh. Any ideas at all? David?
You have to set it up like those problems where you try to find like the percentages of the new.
Okay, so David says, we did something like this before, it wasn't quite that complicated, but where we had, mixed a couple of solutions together, one solution was 10%, one was 11, or 52%, and one ended up with a 23%, remember those? And our strategy at the time was amount times percent plus amount times percent equals amount times percent. Okay, that's what we did before. Okay, let's look at this situation. We can do the same thing, but it's gonna be a lot bigger. Because now I have, okay, one that's 22%. So, okay, x times 22%. I have another one that's 30%. I'll turn it around. And another one that is 42%. So X, Y, and Z are representing the amount of each kind of alloy that I have. Now that has to end up equaling the total amount, which is what? What is my total amount going to be? 80 times the percent of the total, which is 34. So there is the equation. Nice thinking, David, good thinking. There's the equation to start the problem anyhow. Now, I didn't define my variables, but X is the amount of 22%. Y is going to be the amount of 30%, and Z is going to be the amount of 42%. At least that's the way I wrote this equation. Now, how many variables does that equation have? 3. So I need 2 more equations. I need to find 2 more equations in my problem so that I'll have a system like I just had, 3 equations, 3 unknowns. Does anyone see another equation in the problem?
2x equals y.
2x equals y. All right, that looks awfully simplistic. Let's look at it and see. It says the amount of 30% is twice the amount of 22%. And y was the amount of 30%. So the amount of 30 is twice the amount of 22. Yep, there's another equation. Now I got 2. Joseph?
I'm just guessing, but could another equation be x plus y plus z equals 80?
Yes, because don't the amounts have to add up to 80? So that's exactly right, Joseph. Now I have 3 equations. I don't care how you solve it. You can solve this one. You could do some substituting if you wanted. It's completely up to you. By hand, I mean. Or you can set up a matrix and do it either with the inverse method or RREF. If you did set up a matrix, and again, this is completely up to you. One row is going to be 0.22, 0.30, 0.42, and then this is going to be whatever those are times each other. What is 80 times 0.34? 27.2. Does that make sense to everybody, that that would be one of the rows? What would this row look like? 2x minus y equals 0. So we have 2 minus 1, 0, 0. And on the bottom we have 1, 1, 1, 80. Now, if I'm doing this by hand, I'm going to put that row on top. But if I'm given a choice, I'm never doing this by hand. I'm going to type it in on my calculator. But if I were doing cost elimination by hand, you understand you want that row on top? Because of the 1 right there. not have to do it this way. You can use whatever method you want. This is how I would do it, because I like it, but you don't have to do it this way. Did anybody RREF this? Okay, so let's talk about what we got. What is it?
160 over 11. 320 over 11.
You did it last night. Use it different as possible.
Now, I'm gonna wait to see if anybody else got that. He got crazy decimals, I'm sure, so he hit his math frac button and changed it into fractions, so he didn't have to round off. Okay, let's answer the question then. How many grams of each alloy is required? So what are you gonna say? 160 11 grams of the 22%, 320 11ths of the 30%, and 400 11 grams of the 42%. You all right? All right, 7-3 homework will be due on Tuesday. Same day we have our quiz, won't that be on Tuesday? Big day on Tuesday. All right, here we go, 7-4, we're gonna get through a couple of problems, and then I will stop. See how long it takes us. Okay. You are all taking pre-calculus because you all want to eventually take calculus. And there are times in calculus where it is much easier to do the problem, particularly with integrals. If you've heard kids talk about integration, we're doing integration, we're finding integrals. It's easier to do smaller pieces rather than a big chunk. So, when I look at problem number 1 in 7.4, I have a big fraction. So what we do in calculus class is we break this big fraction apart into 2 smaller fractions. Does it make sense to you that I could get this by adding together a fraction that had that as a denominator and that as a denominator? Does it make sense to you that if I were to add 2 fractions with those denominators, I would get one with this denominator? Because those are the factors of this, right? Okay, I have no idea what the numerators are, so traditionally, typically, we just call them A and B. Some little fraction plus another little fraction will give me this big fraction. And if I am integrating, doing integrals, it is much easier to integrate these. Okay? So I need to figure out what those are. So here's what I'm gonna do. I'm gonna, this is a big equation here, a big equation. I'm going to multiply the entire equation by x minus 5 and x plus 3. Why am I doing this? Why am I doing this?
To reduce everything down to like.
I'm going to get rid of the fractions. You're right. It's going to reduce down to no more fractions. They're gone. This is going to cancel and leave me with 5x minus 1. This is going to cancel and leave me with a times x plus 3. this is gonna cancel and leave me with b times x minus 5. Does everybody follow what's happening? Alright, so I'm gonna go ahead and distribute that. So ax plus 3a plus bx minus 5b. I'm just doing the regular distributive property. Now the next step, if it's not obvious to you already, it will be once we talk about it. This is an equation. So the x's on this side have to match the x's on that side. So in other words, 5 has to be a plus b, because this term has to equal these two added together. It's an equation. Similarly, what does -1 have to equal? -1 has to equal 3a minus 5b. Do you see why partial fractions are in this chapter? What do we got? A system of equations. Solve it however you want. I wouldn't mess around with my calculator, although you could. This is a 2 by 2, so you can use substitution, elimination. If you want to put it in your calculator, you can. There's no rule. Do it. Just do it. So let's go ahead. Let's find A and B. Anybody else get A was 3 and B was 2? Now, normally when we solve a system of equations, I want you to write it, anybody wants you to write it like this, because normally when you solve a system of equations, you're looking where the lines intersect each other. Not this time. Our job was to find the two little fractions that add up to this. So the answer to the question will be 3 over x minus 5 plus 2 over x plus 3. This is the answer to the question. Okay, guys? That's the answer to the question. Please make sure that you put whatever your A value was, it goes where A was in the original equation. So A has to go over x minus 5, B has to go over x plus 3. And these, then, are the answer. I want to get some homework handed back, so I guess I'll have to just stop. We'll stop there, we'll pick this up